From a silent world of bare rock and lonely shorelines, to towering forests, sweeping grasslands, and the living green tapestries we know today, plants have spent hundreds of millions of years reshaping our planet in ways both subtle and profound. Hello there, and welcome to the Late Night Scientist channel. Tonight, we'll drift through that entire journey, from the first algae bold enough to touch land, to the rise of forests that breathe life into the air itself. So settle in, let your mind soften, and follow the quiet evolution of plants as they learn to grow, endure, and transform Earth, one patient step at a time. In the long hush of the Precambrian, Earth drifted beneath a sun that felt far too bright for anything daring to step into the open. Almost all life, modest and microscopic, lingered in the oceans where water served as a shield and a cradle. Down there, the world was comfortably dim, stirred by currents that had been repeating the same motions for billions of years. But above the surface lay continents that seemed more like unfinished thoughts, vast plains of bare rock still cooling from the planet's early turbulence, untouched by the softening presence of anything green. Nothing crumbled into soil yet. Nothing held moisture. Nothing swayed in the wind. There wasn't even shade, only the long, unfiltered glare of the sun stretching across lifeless stone. It was a world with plenty of space but no tenants. Land was available, fully vacant, and frankly, rather lonely. The air itself felt unwelcoming. It was certainly breathable to microbes who had perfected the art of resilience, but to anything dreaming of stepping out of the tide pools, it was dry and thin, lacking the layered cushioning that plants would one day build. Without vegetation to break down rock or trap organic matter, the ground remained hard and unfamiliar, offering no softness, no comfort, and no nutrients, only exposure. Any adventurous organism that might have peeked above the waterline would have been greeted by a harsh sun eager to remind newcomers why the ocean was considered the safe neighborhood. Still, Earth was stabilizing in its own slow, methodical way. Volcanic outgassing had shaped the atmosphere. The crust had thickened, and continents had begun drifting into recognizable forms. Oceans expanded and contracted with the cooling of the planet, carving shorelines where shallow water spread like a shimmering invitation. Even without plants, the land was sculpting itself into continents, mountains, and gentle coastal shelves, stage pieces waiting for actors who had not yet evolved. The world felt poised, as if inhaling before the first line of a play. Beneath the waves, cyanobacteria and early algae were already working overtime, releasing oxygen in quantities unthinkable during Earth's infancy. They were not trying to change the planet. They simply couldn't help it. But their byproduct, the slow, steady accumulation of oxygen, was transforming the atmosphere into something more complex and more promising. Over millions of years, this invisible work laid the foundation for future revolutions of life. If plants were ever going to leave the sea, they would need this oxygen-rich air, even if at the moment it felt like unwarranted enthusiasm for a show still missing its main performers. And yet, despite all this planetary preparation, there was silence on land. No rustling, no whisper of leaves, no hum of insects. The only movements were geological, a quiet uplift of a mountain range here, a volcanic exhale there, the slow crawl of continents shifting along their deep, molten currents. Imagine standing on such a world, the horizon vast and empty, the wind uninterrupted by branches, the landscape a monochrome palette of grays and reds where only minerals provided color. Even time itself seemed to stretch differently, without living things to break it into moments. Day blurred into day, and still nothing dared to press roots into the ground that did not yet exist. Yet for all its darkness, the land was not without potential. Rain fell, pooling briefly in cracks before evaporating. Rivers carved channels through stone, rehearsing for the ecosystems they would one day nourish. Sunlight bathed everything freely, as if trying to entice life with a promise of boundless energy. The raw ingredients were here: water, minerals, warmth, atmosphere. What the world lacked was a lineage bold enough, stubborn enough, or possibly clueless enough to try inhabiting a place where survival seemed improbable. But evolution is patient, and life in the oceans had already begun experimenting with forms and strategies that hinted at future possibilities. Some algae clung a little closer to shorelines. Some microbial mats held tighter to rocks exposed at low tide. These weren't plants yet, not in the way we'll later come to know them, but they were testing boundaries, letting the sun fall on their cells a little longer each cycle. What mattered was not success, but persistence. Tiny, incremental steps that would eventually lead to a lineage willing to leave the comfort of the sea. For now, though, these early ancestors kept their ambitions low and their expectations lower. They were explorers in the softest sense, taking the smallest bold steps without knowing they were setting the stage for forests, grasslands, and every flicker of green earth would ever host. As the Precambrian neared its end, land still waited, empty, expectant, and strangely optimistic for a world made of stone. The continents did not know it yet, but their long solitude was nearing a gentle upheaval. Something small and green would soon try its luck at the water's edge, and Earth, patient as always, would be ready to welcome it. In the gentle shallows of the Ordovician world, where land met sea in ragged curves and quiet inlets, something subtle began to happen. So subtle, in fact, that it would have been easy to overlook if we were not watching evolution with patient eyes. Along the edges of tidal pools, faint films of green stretched themselves thin across wet stone, shimmering like watercolor stains. These were algae, familiar in many ways to their aquatic relatives, but something about their behavior set them apart. They lingered where the water retreated. They tolerated the brief moments when sunlight pressed too warmly against their cells. They clung a little longer to exposed surfaces, as if the boundary between water and land was not a warning, but an invitation. For these algae, the shoreline offered opportunities as strange as they were risky. Light was abundant here, far more intense than what filtered down through deeper water. And while too much light could damage their delicate cells, the potential reward was irresistible: energy, captured directly and efficiently. Sunlight was a feast waiting to be claimed by those bold or stubborn enough to withstand it. Of course, evolution rarely frames things in such dramatic terms. Algae were not consciously seeking new territory. But small variations in tolerance, slightly thicker cell walls, pigments that absorbed harsher wavelengths, the ability to hold moisture just a breath longer, allowed some individuals to drift closer to the edge and to survive there. Drying, though, was the true enemy. Water evaporated quickly from surfaces warmed by the sun. And for organisms whose entire existence depended on moisture, desiccation was not a gentle inconvenience. It was a nearly immediate sentence. Each low tide exposed these green films to the wide, unforgiving air, forcing them to hold on to every droplet they could. Some did so by clumping together, forming mats that trapped humidity between their layers. Others flattened themselves against the stone to reduce surface area exposed to the breeze. A few simply endured by sheer evolutionary obstinance, the biological equivalent of refusing to acknowledge the problem until it went away. Those that could not cope disappeared quietly, returning nutrients to the sea. Those that could stayed just a little longer next time. Gravity, meanwhile, behaved as though it had been waiting for this moment with quiet amusement. In the ocean, buoyancy kept everything afloat, gently reducing the weight of living bodies. But here, at the edge of land, gravity asserted itself with full authority, pulling every strand of algae downward. Without water to support them, these organisms sagged, flattened, and stuck themselves to available surfaces, an unintended yet helpful adaptation. Clinging tightly prevented them from being washed back into the deeper sea. Instead, they remained in the zone where water still came and went, not fully aquatic, not fully terrestrial, but suspended in a kind of evolutionary limbo. In these damp margins, life encountered its first taste of unpredictability. Tide pools filled and emptied without warning. Rainstorms soaked everything in sudden abundance. Winds dried the rocks in minutes. The shoreline was a place without routine, forcing algae to develop flexible strategies. Some produced protective compounds to shield themselves from ultraviolet radiation, pigments that would one day become part of the botanical palette inherited by their distant descendants. Others strengthened their outer layers, forming simple barriers against evaporation. These weren't roots or leaves, not yet, but small gestures toward the idea of terrestrial existence. As generations passed, these green films grew thicker and more resilient. They spread across rocks in irregular patches, creating zones where moisture lingered longer than it otherwise would have. In doing so, they subtly shaped their own habitat. Where algae accumulated, they trapped mineral grains and organic debris, creating the earliest hints of something that was not quite soil, but also not just rock anymore. It was a primitive cushion, a softened interface between the living and the lifeless. Though these early innovators lacked any intention, their presence nudged the land ever so slightly toward habitability. And the more they spread, the more they changed the shoreline's chemistry. Through photosynthesis, they released oxygen directly into the thin film of air hovering above the rocks. It wasn't much, barely detectable compared to the ocean's slow atmospheric contributions. But locally, it created tiny pockets of enriched air. For organisms attempting to colonize new territory, even small environmental adjustments can open evolutionary doors. Meanwhile, patches of green grew in unexpected places. Splashed rocks received a misting of seawater with every wave, allowing algae to establish themselves high above the normal tide line. Damp sand held moisture long enough for filaments to weave their way through the grains. Even the undersides of pebbles hosted miniature galleries of clinging life, protected from the sun but still close enough to the water to make survival possible. These microhabitats formed the earliest experimental landscapes for life's cautious advance onto land. With each tide cycle, algae existed in a world of alternating comfort and crisis. Submerged, they thrived effortlessly. Exposed, they endured. This rhythm shaped them, sculpting adaptations that would eventually make true terrestrial plants possible. But these early pioneers were not plants yet. They were still algae, simple, soft-bodied, utterly dependent on moisture, but beginning to explore the idea of independence from the sea. Their greatest evolutionary contribution was not grandeur or complexity. It was curiosity, slow biological curiosity that didn't know it was curiosity at all. If we imagine standing quietly on one of those ancient shorelines, we might see only a faint green shimmer across wet stone. It would seem insignificant, almost accidental. Yet within those thin smudges lay the first whisper of forests, grasslands, and every patch of green earth would one day celebrate. All of it began with algae lingering where they technically shouldn't, insisting that maybe, just maybe, the land deserved a chance. When mosses first appeared on land, they did not arrive with grand architectural ambitions. Unlike the towering forests that would come much later, these early bryophytes embraced a strategy so disarmingly simple it almost felt like a cosmic joke. Stay tiny, stay soft, and stay close to the ground. It was an evolutionary approach rooted not in conquest, but in quiet persistence. A lifestyle built around the idea that you don't need to stand tall to change the world, just long enough to influence it grain by grain. Imagine the young continents at this stage, still raw and rough-edged. Cracks spidered across exposed stone, rain collected in shallow depressions, minerals baked beneath scattered sunlight. Onto this landscape crept the first mosses, forming tufts and films that looked more like delicate fuzz than plants. They lacked true roots, relying instead on hair-like rhizoids that offered only the modest service of keeping them attached to something, rather than feeding them. In a sense, mosses were more guests than owners of the land, but they were guests with remarkable staying power. Their bodies were built for a life of immediacy. Without complicated plumbing systems to move water through stems, mosses absorbed moisture directly across their surfaces. Every leaf was effectively a sponge, willing to drink from dew, rain, or even faint traces of humidity. As long as they were damp, mosses thrived. When they dried, they simply paused. It was a minimalist philosophy. Do what you can with what you have, and when the world becomes difficult, wait politely until conditions improve. This ability to tolerate desiccation beyond anything the algae before them had managed gave mosses a flexibility that transformed the land. They could occupy places where water appeared only in brief, shimmering visits, the tops of rocks, the sides of cliffs, the thin soils accumulating between broken fragments. Anywhere moisture touched, even temporarily, mosses took advantage. And if the rain returned hours or days later, they resumed their soft green work as if nothing had happened at all. Their small stature, far from being a limitation, allowed them to build communities that hugged the ground in layered mats. These mats trapped dust, organic debris, and minerals washed down by rain. Slowly, subtly, the hard face of the continents began to soften. Mosses did not break rock by force. They were not equipped for such drama, but they surrounded it, held moisture against it, and created microenvironments where chemical weathering flourished. Over thousands of years, this gentle pressure turned stone into sediment, and sediment into the earliest true soils. And the moment there was soil, even the thinnest suggestion of it, life had something new to cling to. At close range, these early moss carpets would have been miniature worlds. Each tiny shoot, only millimeters tall, formed narrow corridors where film-like water passed between leaves. In those damp spaces, microorganisms found refuge, thriving in pockets of shade and moisture that had never existed before. Mosses expanded the usable surface of the land not by building up, but by sprawling outward, creating complexity on a scale so small it was easy to overlook, yet fundamental to Earth's transformation. They also found creative solutions for reproduction. Without seeds or flowers, they relied on spores, light enough to ride gentle breezes, but sturdy enough to survive dry journeys. Their sporophytes stood just high enough above the moss beds to give their spores a chance at wider travel. These tiny stalks, topped with capsules, were as close as mosses came to ambition. But modest as they were, they extended the reach of moss communities across continents, allowing patches of green to appear in scattered clusters wherever conditions permitted. In wetter regions, mosses formed expansive blankets that looked like soft, rolling terrain. In drier places, they lived short but repeated lives, growing when moisture allowed, and retreating into suspended animation when the land dried again. Their adaptability allowed them to endure cycles of abundance and scarcity long before more complex plants would attempt similar feats. Mosses also altered the world in ways they never intended. By trapping water, slowing runoff, and holding soil in place, they changed how landscapes responded to weather. Where once rain would have washed freely across bare rock, now droplets were slowed, absorbed, and redirected. Streams ran clearer. Sediment settled where mosses held it. The continents began to develop texture, soft edges where once there had only been sharpness. Life on land, for the first time, found stability. Of course, mosses themselves remained charmingly unimpressed by their accomplishments. They continued to live as they always had, content with minimalism. They made no attempt to grow tall or develop woody stems. They saw no reason to compete for dominance in a world where moisture was unpredictable and conditions shifted often. Instead, they perfected the art of being small, so perfectly, in fact, that bryophytes today remain largely unchanged from their ancient ancestors. Their evolutionary success lay not in innovation, but refinement. The ability to dry out and revive. The capacity to live perched on almost any moist surface. The delicate structures that captured and held water. These traits served them well in landscapes that were still adjusting to life. Mosses became the quiet pioneers of terrestrial ecosystems, not through grandeur, but through persistence. They prepared the land for other plants, without ever imagining such guests would arrive. In their soft, unassuming way, mosses reshaped Earth simply by being present, by insisting that even the harshest landscape had room for green, if that green was willing to grow low and slow. Long before forests reached skyward or roots stitched continents together, the young land remained coarse and unwelcoming, its surfaces uneven, its minerals locked away, its cracks holding only brief flashes of moisture. Mosses had softened pieces of the landscape, but true soil, the kind that could cradle complex life, was still a missing ingredient. It would take a partnership, quiet, ancient, and surprisingly cooperative, to unlock the potential of the continents. And like many great evolutionary collaborations, it began not with a plan, but with two organisms simply trying to make survival a little less difficult. Enter fungi, those understated chemists of the early land. They had crept onto Earth's surface alongside the green pioneers, not seeking sunlight like plants, but nourishment. Anything organic, anything dissolved, anything that offered even a hint of usable energy. Fungal filaments spread through cracks, threading themselves into microscopic crevices, forming networks delicate enough to slip between grains of minerals. They did not need height or leaves. They needed only a surface to explore and a challenge to dissolve. Plants, meanwhile, continued their tentative expansion across damp environments, but they faced a constant obstacle. Without roots capable of reaching deeper or stronger nutrients, growth stalled. The land was rich in potential, but stingy with accessibility. Rock held nutrients tightly, refusing to give them up to organisms that possessed no chemical tools to unlock them. Plants lacked the ability to digest stone. Fungi lacked the ability to photosynthesize. Each had something the other needed, though neither intended a partnership at first. Evolution often works like this. Two strangers discovering by accident that they are better together than alone. Fungal hyphae, the fine threads of early fungi, began brushing up against plant tissues. They wrapped around them, explored their surfaces, and eventually slipped between their cells. To us, this might seem invasive, but for both partners, it was the beginning of something quietly revolutionary. The fungi offered chemical solutions, enzymes capable of dissolving rock, releasing phosphorus, nitrogen, and minerals that had been trapped inside the crust since Earth's formation. The plants, in turn, offered sugars, sunlight transformed into edible currency. It was a trade agreement written without language, signed without signatures, and honored simply because it benefited everyone involved. Slowly, this exchange gave rise to the earliest mycorrhizal relationships, those elegant plant-fungus partnerships that still thread themselves beneath modern forests. But in these early days, The effects were far more dramatic, because the land had never before witnessed such cooperation. As fungal networks expanded, they etched their presence into the rock itself. Enzymes seeped into mineral grains, softening them, prying them apart molecule by molecule. Rainwater then carried loosened particles into small depressions, where plants eagerly claimed the new material. These first flecks of soil were humble, little more than damp crumbs, but they marked the beginning of a transformation that would reshape every continent. Where soil formed, water lingered longer. Mosses held on to freshly loosened sediment, creating thicker pads. Plants with fungal partners grew slightly larger, slightly stronger, slightly more capable of surviving dry spells. Fungi thrived in the shaded moisture that plants provided. The two organisms created a feedback loop, one softening the land, the other stabilizing it. Over generations, this quiet dance carved out environments that felt more welcoming, more hospitable, more alive. Above ground, the process would have been almost invisible, a gradual darkening of the pale rock surface, a dusting of fine particles gathering in sheltered corners, a faint, earthy smell hinting at the changes unfolding. But beneath the surface, the land was being rewritten. Fungal networks mapped the continents in delicate threads, turning barren expanses into hidden laboratories of decomposition and mineral liberation. The continents, once hard and indifferent, began to crumble into textures capable of supporting something more ambitious than low-growing mats. As soil deepened, even by a few millimeters, the impact was profound. Microbial life flourished in the spaces between particles, feeding on organic traces left behind by decaying mosses and fungi. Water pooled into tiny reservoirs during dry moments. Seeds, once they evolved much later, would find these pockets essential, but at this stage, even spores benefited from the moderated environment. The land was slowly becoming a patchwork of microhabitats, rather than a uniform sheet of inhospitable stone. Fungi, ever opportunistic, explored farther. They stretched into new cracks, dissolved new minerals, expanded their partnership with an increasing variety of early plants. Their reach extended beyond what any individual organism could achieve alone. They stitched the land into interconnected webs before plants even dreamed of doing so. In time, these partnerships enabled plants to grow taller, stronger, and more structurally confident. They could finally access nutrients from deeper layers, rather than relying solely on fleeting moisture at the surface. Soil became both a resource and a refuge, a buffer against the whims of weather, a cradle for new growth, and a memory bank of decaying organic matter. Every year added a thin new layer, each generation leaving behind traces that enriched the next. It is no exaggeration to say that soil is the quiet engineer of Earth's ecosystems. Yet its invention was not a single moment of innovation, but a long, accidental conversation between organisms that had no idea they were transforming a planet. Through cooperation, they softened landscapes, thickened riverbanks, and laid the foundation for forests, wetlands, and every terrestrial ecosystem that would follow. Today, when we hold a handful of soil, we cradle the legacy of those early partnerships, millions of years of slow, persistent collaboration. It is a reminder that some of evolution's greatest accomplishments begin not with competition or dramatic leaps, but with two small organisms deciding, through trial and error, that life is simply easier when shared. For millions of years, life on land existed mostly as a quiet, close-to-the-ground affair. Mosses and their relatives spread across softened surfaces, fungi threaded through the soil below, and together they formed a green-brown tapestry no taller than a fingertip. It was a world of smallness, humble, delicate, and mostly horizontal. But evolution, ever curious, began to nudge certain lineages toward a question no plant had yet asked. What if you didn't have to stay low? Sunlight poured down freely. The air was spacious. The world above a few centimeters was entirely unoccupied. And yet reaching upward required something plants had never possessed: a way to get water from the ground to wherever up turned out to be. This is where vascular tissue, Earth's earliest botanical plumbing, quietly stepped into the picture. It didn't appear with any flourish. It began as subtle channels in the stems of small, simple plants, tiny tubes that stiffened their bodies and allowed water to travel higher than surface moisture alone could support. These channels would one day be famous as xylem and phloem, but at the beginning, they were more like experimental doodles in the margins of evolution's notebook. Try this. Might help with height. Xylem, the water-conducting tissue, offered two gifts at once. First, it acted as a pipeline, drawing water from the ground through a steady pull created by evaporation at the plant's surface. Second, it provided rigidity, a scaffolding that kept stems from collapsing under their own weight. Phloem, more delicate but equally crucial, transported sugars and nutrients to the parts of the plant that needed them. Together, these tissues formed the first internal support system, a simple but elegant arrangement that allowed plants to grow not just outward, but upward. With these new tools, early vascular plants emerged onto the Ordovician and Silurian landscapes as slender, branching forms that looked almost architectural in their simplicity. They lacked leaves as we know them. Instead, they sported thin, forked stems, each split a gentle attempt at expanding surface area. Some were barely as tall as a hand. Others reached toward the lofty height of 1/2 meter, giants compared to anything that had lived on land before. Standing upright was still a precarious business. Gravity, ever unimpressed by botanical ambition, pulled on every new shoot, testing the limits of these early structural adaptations. But even a small rise above the ground gave plants access to a world of sunlight that low-growing species could not match. Height came with new challenges. Water had to be drawn farther. Nutrients had to be shared among more cells. And structural failure, a concept rarely encountered by mosses, suddenly became a common occupational hazard. Many early vascular plants simply toppled when they grew too tall too quickly, a lesson that vertical aspirations required restraint. But evolution thrives on such mistakes. Each plant that survived a bit longer passed on its improvements: slightly stronger walls, slightly more efficient transport, slightly better balance. As stems grew taller, the landscape began to change. Sunlight that once reached the ground unimpeded now encountered slender spires of green. Shadows, tiny ones at first, striped the terrain. The air above the soil shifted subtly as plant surfaces slowed wind currents. These changes may seem trivial, but they marked the beginning of ecological layering, the creation of vertical space where none had existed. Here, in the quiet rise of simple vascular plants, the blueprint for future forests took its first tentative shape. The appearance of sporangia at the tips of stems further rewarded this new vertical strategy. Elevated spores caught breezes that plants hugging the ground could never access. Reproduction gained a wider reach, extending the influence of vascular species beyond the slow crawl of ground-level dispersal. Each successful spore that landed on damp earth and sprouted into a new shoot reinforced the idea, once again, an evolutionary notion rather than a conscious one, that height was useful if it could be supported reliably. As vascular plants continued to evolve, they explored more intricate branching patterns. Some developed dense networks of stems that formed low, tangled thickets. Others grew more sparsely, seeking the balance between capturing sunlight and minimizing the cost of additional height. Photosynthesis improved as more tissue was lifted into the open air. Airflow, which cooled and dried exposed surfaces, also made plants more efficient by preventing overheating. Even water uptake improved as vascular systems refined their structure, creating stronger internal gradients that pulled moisture upward with increasing reliability. Beneath the surface, roots began to interact more meaningfully with soil. Though still simple compared to later plant lineages, early roots extended deeper than rhizoids ever could, anchoring plants more firmly and granting them access to buried pockets of water and nutrients. The partnership between fungi and plants, which had already softened the ground, now expanded in complexity. Fungal threads linked to roots, aiding in mineral absorption, while plants rewarded them with sugars. Vertical growth and subterranean cooperation evolved in parallel, each enabling the other. The landscape, once dominated by flat carpets of moss, now featured patches of upright green that swayed with the wind. It was an era of experimentation, a time when plants were learning how to be taller without understanding precisely why height mattered. Every slight increase in stature reshaped the microclimate around it, altering humidity, inviting new tiny organisms to shelter beneath, and gradually creating environments favorable to further diversification. As these early vascular pioneers strengthened their internal frameworks, they laid the groundwork for the extraordinary botanical architectures that would follow. Their humble tubes of water and sugar would one day support trees taller than any animal. But for now, their contribution was quieter, proving that land could be inhabited not only across its surface, but above it. Plants had taken their first confident steps into the vertical dimension. As plants continued their upward experiments, the world beneath them remained a shifting and uncertain foundation. Early soils were thin, easily washed away, and prone to drying. The land might support a tentative shoot or two, but it had no reason to hold anything tightly. Storms carved channels through loose sediment. Winds brushed away exposed grains, and seasonal changes rearranged the ground with quiet indifference. For plants aspiring to rise higher, for those daring little stems now equipped with vascular tissue, survival demanded more than internal plumbing. It required a way to grip the land with intention. This is where true roots emerged, threading themselves downward in a slow but determined search for stability. Unlike the delicate rhizoids of mosses, these early roots were structured for both anchoring and exploration. They grew not merely to hold a plant in place, but to negotiate with the soil itself. Each root tip was a patient explorer, pressing into damp pockets, slipping through narrow crevices, and navigating around obstacles with surprising precision. They sensed gradients of water and nutrients, following them like silent maps written directly into the earth. Evolution did not grant roots their complexity all at once. They began as simple extensions, small forks of tissue pushing downward. But as plants stretched taller above the surface, the demands on their support system increased. A toppled plant could not rely on chance to re-establish itself. Gravity had little sympathy for botanical ambition. So root systems thickened. Their outer layers strengthened. They branched into finer networks, capable of covering surprising distances for such modest organisms. Each new filament increased the plant's reach, offering both nourishment and security. In the dim world below ground, these expanding networks transformed the landscape in ways that were profound but almost invisible. As roots grew, they pushed soil particles aside, loosening compacted ground. They created tiny tunnels where air and water could move more freely. Every space carved by roots became a microhabitat, a pocket of moisture, a home for microbes, a reservoir where dissolved minerals gathered. And when roots died, they left behind hollow pathways that acted as ready-made channels for the next generation. Soil, once an amorphous mix of softened rock and decaying material, now began to develop structure. Roots also entered into deep collaboration with fungi, extending partnerships that had begun earlier in Earth's history. Fungal filaments intertwined with root hairs, vastly increasing the plant's ability to absorb phosphorus and other essential nutrients. In exchange, fungi received sugars and stable living space. Together, they formed networks of astonishing efficiency, able to transfer minerals from one part of a landscape to another in ways no single organism could achieve alone. Below ground, life hummed with quiet cooperation. Above ground, the effects of these roots were gradually revealed. Plants now stood more confidently, resisting the push of wind and the weight of rain. Their roots locked soil in place, preventing erosion and stabilizing riverbanks that had once shifted constantly with every storm. As water traveled across the land, roots slowed its passage, allowing more to seep into the ground rather than racing away in sudden floods. Over time, streams ran clearer, floodplains broadened. Valleys deepened and softened under the influence of plant-driven stability. Landscapes that once changed with chaotic energy now settled into predictable rhythms. As root systems became more intricate, plants discovered the benefit of growing in clusters. A group of rooted plants could stitch the soil into a shared foundation, each root system reinforcing the next. What had once been a solitary effort one plant gripping the ground for itself, became a communal architecture beneath the surface. Entire patches of vegetation moved as unified bodies during storms, swaying but rarely uprooted. In this way, roots not only secured individual plants, but knit communities into living networks. With improved access to nutrients, plants grew larger and more complex. Their stems thickened, their branching patterns diversified, and their reproductive strategies expanded. But none of this could have occurred without the foundations laid underground. Height was impressive, but height without support was simply gravity waiting to happen. Roots provided the counterbalance, the quiet strength beneath every upward gesture. They also altered the chemistry of the world in subtle but important ways. By absorbing minerals and redistributing them through plant bodies, roots participated in nutrient cycling long before animals contributed their own complex behaviors. Plants took in elements from deep within the soil and released them again when they decayed, redistributing nutrients across the land. Over vast stretches of time, roots played a role in shaping the very chemistry of the oceans, as minerals carried by rivers eventually returned to the sea. Roots even influenced the atmosphere, though indirectly. By enabling plants to grow taller, thicker, and more numerous, they increased the amount of carbon absorbed through photosynthesis. Their underground presence slowed the decay of organic material, trapping carbon in soils for longer periods. Planetary climates shifted in response, not overnight, but through the relentless accumulation of tiny contributions. In their quiet way, roots became architects of Earth's stability. They did not seek recognition. Evolution doesn't reward applause. But their presence allowed landscapes to hold their shape, ecosystems to develop layers, and plants to explore form that would have been impossible in a world without anchorage. Every towering tree, every sweeping meadow, every patch of vegetation that withstands the elements owes its existence to those early experiments in holding on. Roots, humble as they seem, marked the moment when plants truly claimed the land, not as temporary visitors, but as residents capable of shaping it from below. When the Carboniferous period unfurled across Earth, it brought with it one of the most dramatic botanical revolutions the planet had ever seen. The once modest vegetation, which had spent millions of years quietly refining its support systems, suddenly found itself with everything it needed to attempt a feat no plant lineage had dared before: the creation of forests. Not scattered groves, not thickets or low carpets of green, true forests, dense and towering, where sunlight filtered through layered canopies and shadows stretched across waterlogged ground. It was a world in which plants discovered height not as a novelty, but as an identity. These early forests did not resemble the leafy woodlands familiar to us today. Instead, they were dominated by giants with strange anatomies and stranger life cycles, lycophytes with scaly trunks, horsetails as thick as a person's arm, tree ferns unfurling fronds longer than a doorway. Some of these plants reached 30 meters into the air, building the first vertical ecosystems Earth had ever seen. Their trunks rose from swampy soils like green columns, their crowns forming interconnected roofs that swayed as single living structures when storms passed overhead. For the first time, the continents echoed with the quiet creak of wind through many layers of vegetation. The swamps where these forests thrived were endlessly dynamic. Rainfall fed broad wetlands, river channels shifted unpredictably, and groundwater seeped up to the surface in shimmering pools. The land was saturated, dark, and rich in nutrients, a perfect canvas for plants that reproduced by spores rather than seeds. Moisture was abundant enough for spores to travel, settle, and sprout. Without the delicate packaging, future plants would evolve. The forests took advantage of this environment with enthusiasm, producing enormous quantities of spores that drifted through the air like greenish-brown mist. In quiet moments, one could imagine the world exhaling clouds of botanical possibility. The trunks of these ancient giants had unusual structures, often hollow or filled with soft pith. Their support came not from wood in the modern sense, but from thick layers of specialized cells that stiffened the outer walls. Many relied on sheer diameter to remain upright, growing wide rather than intricately branched. Their surfaces were patterned with diamond-shaped scales or spiraling ridges, textures hinting at evolutionary experiments that would never be repeated once seeds later reshaped the plant kingdom. Everything about these forests conveyed a sense of provisional grandeur, as if evolution had sketched these early trees with bold strokes before refining its techniques in later ages. The atmosphere of the Carboniferous was profoundly influenced by these towering ecosystems. As forests expanded, photosynthesis intensified. Plants absorbed carbon from the air and buried much of it when they died, layering thick beds of organic matter in the oxygen-poor swamp bottoms. Over millions of years, these layers would compress into coal, leaving behind the geological record of a world that once pulsed with botanical abundance. With so much carbon locked away, atmospheric oxygen rose to levels higher than at any point before or since. The very air of the Carboniferous felt different, denser, more energetic, almost eager for combustion. Even the smallest spark could encourage flames to leap enthusiastically through dry patches at the forest edge. The forests, however, were far from still. They were places of constant vertical motion. Spore stalks stretched upward, competing for the narrow windows of sunlight that pierced the canopy. Fern fronds unfurled slowly, their curled tips rising like gentle question marks before opening into wide fans. Vines climbed opportunistically, using the trunks of larger plants as ladders toward the brightness above. The world felt layered, textured, alive in 3 dimensions. Even decomposition, slowed by waterlogged soils, contributed to the depth of the landscape. Fallen trunks accumulated in stacks, forming natural dams and creating new pools where future forests would take root. These environments shaped the evolution of countless organisms, including early arthropods that scuttled across the forest floor or took to the air with newfound size. The oxygen-rich atmosphere allowed insects to grow larger than anything comparable today. Dragonflies with wingspans wider than a human arm glided between towering trunks, their movements marking the first true aerial ecosystems. Though plants themselves were unaware of the biological ripple effects they caused, their towering presence created opportunities that spread far beyond the botanical world. But the forests also faced challenges. Their immense size made them vulnerable to shifts in water levels. Floods drowned root systems. Droughts exposed trunks to catastrophic collapse. Lightning strikes in the oxygen-heavy air could ignite vast fires, transforming entire swaths of forest into smoldering plains. Yet destruction only prepared space for new growth. Spores colonized burned areas with remarkable speed, and within a few short generations, young plants reached skyward again. These forests evolved not through delicate control, but through cycles of growth, collapse, and renewal. Deep below their towering forms, roots and fungal partners wove dense webs that held soil in place and slowed the movement of water through the swamp. This created zones of surprising stability within otherwise shifting landscapes. Over time, layers of dead plant material accumulated so thickly that new growth rooted directly into the remains of its ancestors. Forests built upon forests, each generation layering the land with more organic matter. It was as though the planet had discovered a way to store the memory of green life in its own sediment. To wander through a carboniferous forest, were we able, would be to step into a twilight world where the sun reached the ground only in fragments, where humidity clung to every surface, where the air smelled of living foliage and slow decay. It would feel ancient even then, as though life had suddenly expanded into a dimension it had long been waiting to explore. And in a sense it had. Plants had learned to conquer height, and with that triumph came a new chapter in Earth's unfolding story. A world no longer defined by empty landscapes, but by the towering, breathing presence of green. As Earth's early forests rose into the carboniferous sky, plants found themselves navigating an increasingly intricate world of light and shade. What had once been a planet, bathed evenly in sunlight, was now a patchwork of brilliance and dimness. Beams filtering through towering trunks, shimmering on wet ground, and disappearing again behind layered canopies. For plants growing beneath these green skyscrapers, light became both a resource and a puzzle. How could they capture enough of it to thrive while also managing the risks that came with exposure? To solve this dilemma, evolution introduced one of its most elegant inventions, the leaf. Leaves did not spring into existence fully formed. They began as small expansions along stems, subtle flares that increased surface area just enough to give their owners a competitive edge. Over thousands of generations, these modest flaps widened, lengthened, and flattened, eventually becoming broad solar panels capable of capturing light with astonishing efficiency. But this increase in size brought a new vulnerability: drying. A large surface area invited sunlight, but it also encouraged water to escape into the air. Plants suddenly faced a balancing act they had never encountered on this scale: how to breathe without dehydrating. Enter stomata, the tiny, adjustable pores that transformed plant physiology forever. Scattered across leaf surfaces like delicate valves, stomata could open to allow gases to flow, letting carbon dioxide in and oxygen out, and then close again to conserve moisture. It was a remarkably sophisticated system for organisms without nerves or muscles. Each stoma responded to environmental cues such as humidity, light intensity, and internal water pressure. When conditions were favorable, stomata opened wide, and the leaf became a bustling center of photosynthetic activity. When conditions changed, the pores narrowed or sealed shut, saving precious moisture. Plants had learned to breathe with intention. This innovation allowed leaves to grow larger and thinner than ever before. Sunlight could penetrate deeper into layers of cells, fueling photosynthesis with newfound efficiency. At the same time, the network of veins inside each leaf, a refined extension of the vascular system that had once supported only stems, delivered water to every corner, ensuring that photosynthetic tissues remained hydrated. These veins also carried sugars away from the leaf, distributing energy throughout the plant. Leaves became not merely sunlight collectors, but bustling hubs of chemical exchange, the engines that powered plant growth on a scale previously unimaginable. As leaves broadened across Earth's landscapes, they reshaped ecosystems from the canopy down to the forest floor. In dense forests, layered leaves created a tiered world of light. Some plants thrived in the canopy, where sunlight was abundant, but water evaporated quickly. Their leaves developed protective coatings or narrow shapes to manage the heat. Others specialized in the understory, producing wide, delicate leaves designed to catch even the faintest glimmers filtering through the greenery above. Shade-tolerant species flourished in these diffused light zones, turning dimness into opportunity. A new diversity of plant forms emerged, each leaf type a response to the mosaic of light created by its neighbors. With leaves came greater influence on the atmosphere itself. As stomata opened and closed across billions of square meters of leaf surface, they collectively controlled vast exchanges of water vapor and carbon dioxide. Transpiration, the release of water into the air through stomata, became a defining force in climate and weather patterns. Forests began to generate their own humidity, shaping rainfall and cooling their surroundings. Air moved differently through dense foliage than it had across bare ground, swirling in gentle eddies that distributed moisture and moderated temperature. Leaves were not just responding to the world, they were influencing it. The presence of broad leaves also invited a host of new ecological interactions. Insects, which had flourished in the high-oxygen atmosphere of the Carboniferous, now encountered an abundance of nutritious surfaces. Some fed on leaf tissue directly, others sheltered beneath it. This relationship, though occasionally inconvenient for plants, spurred evolutionary adaptations such as tougher epidermal layers, bitter chemical defenses, and intricate leaf shapes that discouraged grazing. In return, insects unwittingly assisted with spore dispersal, carrying reproductive material from place to place as they climbed and fed. The world grew more interconnected, more dynamic, as every leaf became an opportunity for both cooperation and conflict. Not all leaves, however, lived in the same way. Some evolved intricate drainage patterns to shed water efficiently during rainstorms. Others arranged themselves to avoid shading one another, angling with graceful precision toward patches of sun. Some thickened and curled, storing water for dry periods. Each form reflected a delicate balance between capturing light and conserving water, a balance made possible by the quiet choreography of stomata. opening and closing in response to the changing breath of the environment. As these innovations spread, landscapes once dominated by towering stems took on new textures. Where early forests had formed simple vertical columns, later ecosystems became a tapestry of layered foliage, broad leaves overlapping like scales, ferns reaching into open spaces, and canopy species forming interconnected mosaics overhead. Sunlight no longer reached the ground freely. It arrived filtered, softened, fragmented into golden shafts that danced with every breeze. This transition marked a profound shift in Earth's history. Plants were no longer just mastering height. They were mastering the interface between themselves and the atmosphere. With every leaf that unfurled, the planet grew more capable of supporting complex life. Shade became a resource. Humidity became a predictable presence. Temperature became moderated by expanses of living green. Leaves, in their quiet way, became architects of comfort for countless species that would emerge in their shadows. From small flares along stems to broad, breathing surfaces that shaped entire climates, leaves rewrote the rules of terrestrial life. They taught plants how to manage abundance, sunlight, water, and air, and how to thrive in the delicate balance between them. For millions of years, plants lived under a quiet but persistent constraint. Reproduction required water. Spores, delicate and eager as they were, needed damp surfaces to germinate and moist environments to meet their complementary partners. This limitation kept even the tallest forests tethered to conditions that could shift overnight. A dry spell could unravel generations of patient growth. A shifting landscape could strand entire lineages in places where their spores had no hope of finding what they needed. Plants had conquered height, light, and soil, but they were still beholden to moisture's whims. Then evolution offered a remarkable new invention: the seed. Modest at first glance, but transformative in nearly every way, the seed was a package of potential wrapped in security, a portable cradle carrying both nourishment and a living embryo, built to endure uncertainty rather than surrender to it. Where spores represented hope tossed into the wind, seeds were a deliberate investment in the future. The earliest seeds appeared in environments that had begun to dry and fluctuate. Rivers wandered across landscapes differently than in earlier eras. Wetlands retreated during certain seasons and surged during others. Forest floors alternated between saturation and desiccation. Plants needed a way to reproduce without gambling everything on the presence of water at precisely the right moment. Seeds offered that freedom. They protected the embryo from drying, from cold, from hunger. A seed could wait for months, years, even longer, holding its quiet breath until conditions gently invited it to grow. Unlike spores, which were exposed to the full force of the world the moment they landed, seeds traveled with a built-in pantry. Inside each one, nutritious reserves sustained the embryonic plant through the earliest, most vulnerable stages of life. These reserves, wrapped in protective coats of varying toughness, allowed the seedling to root itself before asking the environment for anything more. No longer forced to sprout immediately or perish, seeds embodied patience. They transformed survival from a desperate race against evaporation into a carefully timed negotiation with the landscape. As seed plants, early gymnosperms, began to spread, the world subtly reshaped around them. Their reproductive process involved pollen, a dry form of male gamete capable of traveling through air rather than across water. When pollen reached the ovule and fertilization occurred, the developing seed matured within protective structures that varied from lineage to lineage. Some plants enclosed seeds in woody cones, others nestled them in exposed clusters. But regardless of form, the outcome was the same: a durable vessel capable of traveling farther and surviving harsher conditions than any plant reproductive unit before it. This newfound mobility opened vast swaths of terrain that had long been inaccessible. Plants could now colonize slopes, uplands, and interior continental regions where moisture fluctuated unpredictably. Dry seasons no longer spelled reproductive disaster. Seeds simply waited. In some environments, entire carpets of them accumulated beneath parent plants, forming quiet seed banks where countless futures lay dormant. Rainfall transformed these banks into miniature germination events, waves of seedlings emerging with synchronized precision, each one drawing from a plan written long before the weather's cooperation. Seeds also encouraged diversity and dispersal strategies. Some were small and light enough to ride the wind, tumbling far from their origins in swirling air currents. Others grew larger and relied on gravity, rolling into crevices or settling in sheltered depressions. Still others developed sticky or spiny surfaces that clung to passing animals, unwitting couriers who redistributed seeds across growing territories. Even plants that lacked wings, hooks, or elaborate designs benefited from the simple fact that seeds could be transported without damage. Whether they traveled inches or miles, they traveled with everything they needed tucked safely inside. With time, seeds changed the vegetation of Earth in ways that were as sweeping as they were subtle. Seed-bearing plants expanded their presence into climates that had once challenged spore-reliant lineages. In cooler regions, seeds overwintered beneath snow. In arid areas, they endured dry spells by slipping into dormancy. In disturbed landscapes, those reshaped by windstorms, floods, or erosion, seeds waited in the soil, ready to reclaim territory with resilience that seemed almost strategic. Plants no longer relied solely on perfect conditions to thrive. They relied on endurance and the art of timing. This shift also affected animal life. Seeds, with their nutrient-rich stores, became valuable food sources. Insects gnawed on them, burrowing into their shells to reach the dense reserves within. Small vertebrates fed on them as well, sometimes destroying them, sometimes inadvertently aiding dispersal by dropping or caching them in new places. Though evolution had not crafted seeds with animals in mind, the relationship would eventually grow far more intricate. But that part of the story belonged to later chapters. Seed-bearing plants developed forms well-suited for this broader, more variable world. Many grew sturdy trunks and robust branches, bearing cones that released seeds seasonally or in response to environmental cues. Others produced clusters of seeds that spilled with the slightest breeze. Their architecture emphasized persistence: thick bark to withstand weather, resinous compounds to deter pests, and branching patterns that made the most of available sunlight. Height was still useful, but now it was paired with an ability to reproduce even in dry or unpredictable years. Perhaps the most extraordinary feature of seeds was their capacity for waiting. While spores were fragile travelers on borrowed time, seeds embodied long-term planning. Again, not by intention, but by evolutionary consequence. A seed could rest through drought, outlast cold, resist decay, and greet the world when it was ready. In a universe where conditions often changed abruptly and without warning, seeds offered plants the rare advantage of flexibility. With the arrival of seeds, plants shifted from opportunists to strategists. They became less dependent on chance and more capable of shaping their distributions through time. Across continents, forests of seed-bearing plants began to replace older, spore-driven ecosystems, not through conquest, but through quiet, patient persistence. A portable future had arrived, packed neatly into small, unassuming shells. As Earth's climates shifted through the late Paleozoic and into the Mesozoic, the botanical world faced a new set of challenges. Regions that were once warm and reliably wet began experiencing greater extremes, colder winters, drier summers, and landscapes where moisture vanished before plants could fully make use of it. For many species, these fluctuations meant hardship. But for the lineage that would become conifers, they were invitations, openings for innovation in the art of endurance. Conifers belonged to a group of seed plants that had already shed dependence on moisture for reproduction. But they did something further. They refined every aspect of their structure to withstand environments where life needed to be cautious, patient, and deeply resilient. Their first innovation was perhaps their most iconic, needle-shaped leaves. These slender, tough structures were narrow not out of aesthetic minimalism, but because narrowness conserved water. Broad leaves, for all their photosynthetic efficiency, lost moisture quickly. Needles, wrapped in waxy coatings and built with tightly packed cells, held onto water as if it were treasure. They functioned slowly but steadily, photosynthesizing whenever conditions allowed, without the frantic need to rush before drying out. The shape of a needle also helped conifers survive wind, snow, and cold. In northern climates, winter storms buried plants in layers of ice. Broad leaves would have snapped under such weight, but needles allowed snow to slip between them, sparing the branches from heavy loads. Their internal tissues resisted freezing more effectively than those of many other plants, using resins and other compounds to prevent ice from damaging cells. Conifer needles, in a quiet way, perfected the ability to endure rather than retreat. Their branching patterns further enhanced survival. Many conifers adopted spires or pyramidal shapes, forms that shed snow efficiently and allowed light to reach lower branches even when the canopy thickened. In drier regions, some evolved open, airy crowns that reduced heat buildup. Nothing in their form was accidental. Everything leaned toward persistence over speed. But conifers' true genius lay beneath the bark. Their wood, rich in resins, provided strength and protection against decay. Resin seeped into cracks and wounds, sealing them with remarkable efficiency. Insects and fungi found this sticky, aromatic barrier uninviting, and predators that pierced the bark were often met with a slow-moving river of defensive chemistry. The scent of resin, carried on wind or warmed by sun, became one of the ancient Earth's most distinctive fragrances, a quiet announcement that the trees emitting it were built for the long game. Conifer trunks grew wide and dense, prioritizing structural integrity over rapid expansion. Their growth rings reflected the cautious pace of their levas, narrow, steady increments that told stories of endurance through unpredictable seasons. In landscapes where fires swept through periodically, thick bark protected their inner tissues from heat. Some conifers even relied on fire as part of their reproductive strategy. Their cones, sealed with resin, opened only after intense warmth released the seeds within. These species did not fear fire. They planned for it. To reproduce, conifers developed woody cones, structures that protected developing seeds from dryness, cold, and hungry herbivores. Each scale on a cone acted like a shutter, keeping the seeds safely hidden until conditions encouraged release. In some species, cones loosened gradually over months. In others, they held their seeds for years, waiting for the precise signal that the world was ready. Wind carried pollen between trees with sweeping efficiency, and the seeds themselves traveled far, sometimes gliding on narrow wings that spun gently through the air. Conifer forests reshaped Earth's ecology. In northern latitudes, they created vast taigas, endless belts of green stretching across continents, forming one of the largest terrestrial biomes in history. These forests were quiet, their understories sparse because needles decomposed slowly and released nutrients reluctantly. The air among them was cool, resin-scented, and filled with soft sound, the whisper of wind, the creak of branches, the occasional fall of snow. In mountainous regions, conifers took root in thin soils and sheer slopes where other trees could not survive. Their roots anchored loose rock and prevented erosion, stabilizing cliffsides and riverbanks alike. In drier climates, conifers developed even more subtle strategies. Some species grew deep roots to reach buried water sources. Others spread wide, shallow networks to catch rainfall before it evaporated. They paced their growth through droughts, slowing metabolism until more favorable conditions returned. While many plants responded to hardship with rapid changes or dramatic die-off, conifers seemed to take challenges as gentle suggestions to pause, breathe, and wait. Their lifespans reflected this approach. Some conifers lived for several centuries, others for millennia. Bristlecone pines, for example, grew slowly on windswept mountains, twisting into sculptural forms as they endured centuries of cold and dryness. Their rings, barely visible, marked time with an almost meditative slowness. These trees witnessed not just seasons, but ages. Despite their caution, conifers were not rigid. They adapted across continents, diversifying into species suited for a vast range of climates, from foggy coasts where moisture drifted in from the sea, to high alpine ridges where temperatures rarely rose above cool. Some species developed scales instead of needles. Some grew into towering pillars like redwoods. Others became low, spreading shrubs that hugged the ground against harsh winds. What united them was their commitment to endurance, an evolutionary philosophy that valued stability, patience, and resilience over speed or extravagance. Conifers proved that thriving did not always require rapid innovation or dramatic change. Sometimes, survival meant enduring what others could not. They became icons of perseverance in a world that was constantly shifting, and their success set the stage for even broader botanical experimentation in the ages to come. By the time conifers had mastered endurance and spread across vast swaths of Earth, the stage beneath them was shifting, literally. Continents, which had once clustered into ancient supercontinents, began drifting apart with slow but irresistible force. What had been familiar coastlines fractured into new shapes. Mountain ranges rose where flat plains had once stretched. Oceans widened, narrowed, and redefined the very edges of the world. For plants rooted in place, this movement might have seemed like a cosmic prank. The world they depended on kept sliding away beneath their feet. Yet in this vast rearrangement lay one of evolution's greatest opportunities. Isolation, though inconvenient in the moment, sparks creativity. As the continents wandered, climates shifted like curtains being drawn across the planet. Regions that once basked in equatorial warmth drifted toward cooler latitudes. Moist coastal plains became arid interiors. Tropical belts stretched or compressed depending on the angle and speed of continental drift. Plants, rooted firmly where chance had placed them, were forced to meet these changes with ingenuity rather than escape. Populations separated by the slow march of tectonics found themselves living in distinct worlds, and over millennia they began to diverge, quietly, patiently, beautifully. Some regions grew wetter as new mountains trapped moisture-laden winds. Here, plants adapted by broadening leaves and developing canopy structures that thrived under near-constant rainfall. These forests became lush and layered, filled with species that mastered shade, humidity, and rapid nutrient cycling. Roots sank deep, partnering with increasingly intricate webs of fungi that evolved alongside them. The rhythm of life in these places became quick and abundant, a sharp contrast to the slow pulse of conifer-dominated lands elsewhere. Other regions, however, drifted into dryness, where rainfall dwindled and seasons fractured into extremes. Plants in these emerging arid zones faced pressures no ancestor had prepared them for. Water-saving strategies diversified. Some species thickened their stems into reservoirs. Others reduced their leaves to scales or spines. And still others formed deep or sprawling root systems that harvested every drop of moisture that touched the soil. Subtle variations accumulated into pronounced specializations. Branches angled to minimize exposure. Surfaces reflected sunlight. Life cycles shortened to take advantage of brief wet periods. Isolation sculpted these lineages into forms that bore little resemblance to their cousins across the sea. Elevation introduced another dimension of divergence. As tectonics pushed continents upward, mountains became laboratories of rapid adaptation. A valley and a peak might be separated by only a day's walking distance, yet they experienced climates as different as distant regions. Plants modified their growth cycles to match short alpine summers, developed antifreeze-like compounds to survive freezing nights, and adapted compact forms to withstand relentless wind. Generations unfolded against the solitude of thin air, shaping sturdy, slow-growing species that clung to cliffsides or nestled in meadows that thawed only briefly each year. On newly formed islands, the story grew even stranger. Continental fragments, volcanic peaks, and uplifted seamounts became isolated realms where a single seed, delivered by wind, wave, or a forgetful bird, could begin a botanical dynasty. With no competitors or predators familiar to their lineage, plants experimented with forms that would seem eccentric anywhere else. Some grew enormous in the absence of grazers. Others shrank into miniature versions of their relatives, perfectly scaled to the limited resources of island life. These isolated ecosystems produced lineages so distinct that returning them to their continental cousins would have prompted puzzled glances, at least metaphorically. Plants are famously polite about family differences. Continental rearrangement also reshaped wind patterns, river systems, and ocean currents. As climates became more patchy, plants optimized themselves to local conditions. A forest that once stretched unbroken across thousands of miles split into mosaic pockets, each evolving under its own set of rules. Over time, these pockets formed biomes, deserts, savannas, temperate woodlands, alpine tundras, and rainforests. Each biome held plants uniquely tuned to its rhythm, and each plant lineage carried subtle echoes of the ancient ancestors from which it had branched. Even the soil changed. As mountains eroded, they fed minerals into surrounding plains. As oceans advanced and retreated, they deposited layers of nutrient-rich sediments. Plants responded to these differences with root systems tailored to the chemistry beneath them. Some thrived on nutrient-poor sands by forming extraordinarily efficient nutrient pipelines. Others reveled in volcanic soils so rich that growth became almost exuberant. The earth beneath plants had always shaped their destiny, but now it did so with a complexity that encouraged endless diversification. Climate oscillations, ice ages, warm spells, monsoon shifts added further texture to this evolving world. Glaciers advanced and retreated, grinding landscapes into new forms and forcing plants to track suitable climates across changing terrains. Species migrated slowly, spreading seeds just far enough each generation to keep ahead of encroaching cold or advancing heat. Some survived these shifts through flexibility, others through tough endurance, still others by shrinking into refuges where conditions remained stable enough for survival. After each climatic turbulence, the survivors carried traits that reflected their journey. What made this era remarkable was not simply the creation of new plant lineages, but the ways in which these lineages crafted entirely new ecosystems. As plants adapted to local conditions, they shaped those conditions further, creating shade where none had existed, building soils where bare stone once lay, altering humidity, influencing fire cycles, and constructing habitats that animals would later depend upon. Regional differences deepened as plants left their signatures on the landscapes they inhabited. Continental drift did not just scatter plant families across the globe. It gave each group room to imagine what else it could become. Where one lineage developed tough needles, Another developed succulent stems. Where one produced cones built for fire, another forged leaves drenched in rain. The world became a patchwork of botanical dialects, each speaking its own version of adaptation. A planet rearranged became a planet reinvented. For millions of years, the plant world had operated with admirable simplicity. Conifers unfurled quiet resilience. Ferns and their kin scattered spores to the mercy of the wind. And seed-bearing gymnosperms relied on breezes rather than precision to find mates. It was effective, if a little impersonal. Then, in the early Cretaceous, evolution unveiled an invention so unexpected and so elegant that it would reshape nearly every ecosystem to come: the flower. Flowers did not burst onto the scene in a riot of brilliance. Their earliest forms were modest, clusters of specialized leaves arranged in patterns that only hinted at the diversity to come. But their purpose was revolutionary. Flowers were communication made biological. They signaled, lured, advertised, and persuaded. They were invitations written in scent and color, designed not for the wind, but for eyes and antennae. At the heart of every early flower was a simple goal: precision. Wind pollination was serviceable but wildly inefficient. Too many grains were wasted, too many opportunities scattered haphazardly into the air. But if plants could entice creatures already moving through their habitats, small insects, early beetles, nimble flyers, to carry pollen directly from one bloom to another, they could drastically improve their chances of fertilization. In exchange, they offered something irresistible: nectar, fragrant oils, nutritious pollen, even sheltered resting places. Thus began a partnership that would reshape not just botany, but the animal kingdom as well. The earliest flowers were subtle, their colors muted, their structures relatively simple, their scents faint but intriguing. They evolved in a world already buzzing with arthropods searching for food, warmth, or temporary refuge. For these creatures, flowers were like little biological taverns offering refreshments, sweet liquids or edible powders packaged neatly where any wandering insect might stumble upon them. And once insects began visiting, carrying pollen grains accidentally on their bodies, the plants refined their designs. Petals elongated, curled, and layered themselves into shapes that guided visitors to precise landing zones. Colors differentiated, first appearing as faint pigments that darkened over time into the reds, yellows, blues, and purples recognizable today. Many early insects couldn't see the full spectrum of human visible color, so flowers communicated in ultraviolet, painting hidden bullseyes and patterns that acted like runway lights. Even the textures of petals evolved, some velvety to grip tiny feet, others smooth to usher visitors toward the nectar chamber. Scent became another medium of persuasion. Some flowers developed gentle sweetness that drifted softly through the air. Others crafted fragrances layered with chemical complexity, detectable from remarkable distances by insects with sensitive antennae. A flower's scent told a story. Food is here. Visit soon. This bloom is ready. It was a message broadcast in molecules. Once insects became regular visitors, Angiosperms diversified with astonishing speed. Each lineage found its own way to court pollinators. Some flowers opened at dawn to match the activity patterns of early foraging species. Others bloomed at night, unveiling pale petals that glowed faintly under moonlight to attract nocturnal allies. Nectar spurs lengthened to accommodate insects with equally elongated mouthparts, an evolutionary duet in which each partner shaped the other. The more tailored the match, the more reliable the pollination. Plants that grew in open, windy landscapes took advantage of bright colors to be seen from afar. Those in dense forests developed deep, tubular blossoms that funneled scent and guided pollinators through dim light. Even the placement of flowers on stems shifted in countless ways. Clustered for impact, spaced for precision, drooping to protect contents from rain, or perched at the ends of branches like tiny lanterns. As these partnerships deepened, pollinating animals adapted in parallel. Insects developed specialized hairs to collect pollen more efficiently, tongues suited to different nectar depths, and flight patterns optimized for visiting multiple blooms. Flowers, in turn, responded with further refinements, pollen grains that stuck better, nectar compositions tuned to specific tastes, and reproductive structures positioned at exactly the right height for pollinion transfer. Evolution had created a dialogue, and both sides were endlessly refining their linguistic skills. Flowers also changed the architecture of plants. Because pollination became more reliable, angiosperms no longer needed to invest as heavily in producing enormous quantities of pollen. Instead, they redirected energy into growing faster, colonizing new habitats, and crafting fruits, structures that protected seeds and enticed animals to aid in dispersal. This shift allowed flowering plants to spread into environments once dominated by older lineages. Grasses, shrubs, vines, and broadleaf trees all descended from these early innovators, each applying the flower's template in its own way. One of the most remarkable outcomes of flowering plants was the emergence of ecological intimacy. Pollinators began depending on certain blooms for food, and blooms depended on specific pollinators for reproduction. It was not a rigid dependency. Nature avoids contracts that cannot be broken, but rather a mutual shaping. Where insects diversified, flowers diversified alongside them. Where flowers flourished, insects followed. This relationship created landscapes rich in seasonal rhythms. Meadows burst into bloom with predictable precision. Forests unfolded glossy buds that opened just as their pollinator partners began their yearly rounds. Even deserts developed patterns of sudden floral abundance when rare rains arrived, transforming barren expanses into ephemeral banquets for bees, beetles, and early wasps. The rise of flowers also brought a new sensory dimension to Earth's ecosystems. Before angiosperms, the land held its own subdued palette: greens, browns, and the soft textures of spores and cones. Flowers introduced bursts of color, sudden fragrances, and fleeting displays that transformed the visual and aromatic character of terrestrial life. The world became, in a literal and metaphorical sense, brighter. Though flowers may seem delicate, their evolutionary impact was anything but. They gave plants a way to communicate through beauty, to negotiate through nourishment, and to collaborate with animals in shaping the next chapter of life's story. Every bloom was, and still is, an invitation, crafted with evolutionary patience and artistic flair. When flowers first appeared, they invited animals into a delicate exchange of pollen and nectar, a quiet conversation between plant and pollinator. But soon evolution introduced a second, far bolder form of communication. If flowers whispered, fruits made offers, not threatening ones but temptations, bright colors, irresistible scents, soft flesh, and hidden rewards. It was a strategy so clever that it bordered on mischievous. Plants had learned to bribe animals into becoming gardeners. The earliest fruits were modest things, simple structures surrounding seeds, offering little more than a marginal improvement in protection and dispersal. But once animals began interacting with them, fruit evolution accelerated. Plants quickly discovered that by wrapping their seeds in something tasty, they could coax creatures into carrying those seeds far beyond the reach of wind or chance. In a world shaped increasingly by movement, flight, climbing, burrowing, roaming, fruits offered the rare ability to hitch a ride inside another living body. To make this strategy viable, plants refined fruits into exquisite invitations. Color became one of their loudest tools. Unripe fruits often remained green and inconspicuous, blending into foliage, essentially saying, "Not yet." But when seeds matured and were ready to depart, the outer tissues transformed. Reds, oranges, purples, and blues emerged, signals tuned to the visual systems of creatures likely to eat them. Birds, in particular, were drawn to bright hues. Mammals responded to scent, sweetness, and texture. Insects targeted smaller, softer fruits designed with their scale in mind. Each fruit was a beacon, a biological advertisement tailored to the species plants hoped would play courier. Inside the fruit, sugar became the primary incentive. Plants had historically used sugars for internal energy transfer, but fruits redirected this resource outward as a lure. Some trees even timed seasonal fruiting to coincide with periods when animals were hungriest or most mobile. In temperate zones, late summer and autumn fruits offered meals precisely when migrating birds needed fuel. A coincidence so convenient it's hard not to suspect plants of cunning seasonal planning. In tropical forests, fruits ripened in staggered succession across the year, creating a living calendar that animals learned to follow. Texture added another layer of persuasion. Soft fruits invited immediate consumption. They dissolved easily, leaving seeds behind in the digestive tract. Hard fruits appealed to animals with stronger jaws or specialized feeding behaviors, creatures willing to gnaw through protective shells. Some plants wrapped their seeds in layers so sweet that animals tolerated the chore of cracking them open. Others coated seeds with slippery or resilient casings that passed harmlessly through digestive systems, ensuring the seed was deposited, sometimes miles away, in a package of nutrient-rich fertilizer. This strategy did more than move seeds. It positioned them with surprising accuracy. A bird perched on a distant branch, a primate wandering into a new grove, a grazing animal seeking shade along a riverbank. all unknowingly planted the next generation of fruit-bearing plants. Over time, these partnerships shaped entire landscapes. Certain tree species became common along migration routes. Others clustered near watering holes or pathways carved by large herbivores. Plants did not follow animals consciously, of course, but evolution arranged their incentives so efficiently that it often looked intentional. Some fruits evolved for creatures that never intended to eat them. Burrs and hooks appeared, small, dry, tenacious structures that clung to fur and feathers with remarkable commitment. These hitchhikers relied not on taste, but persistence. A wandering mammal might collect dozens of hitchhiking seeds on a single stroll, scattering them with each scratch or shake. It was dispersal through annoyance, a strategy that plants perfected with surprising enthusiasm. But not all fruits relied on animals that walked the ground. Many discovered the utility of flight, not by flying themselves, but by prompting birds and bats to carry their seeds across valleys, mountains, and even oceans. In tropical nights, bats became some of the most effective seed couriers on Earth, consuming fruits beneath moonlit canopies and later depositing seeds in new growth-ready clearings. Their nightly routes expanded the reach of countless plant species far beyond what the plants could have accomplished alone. The landscapes themselves reshaped in response. As fruits diversified, so too did the animals drawn to them. Species that once ate insects adapted to frugivory, their digestive tracts adjusting to high-sugar diets. Some animals developed keen color vision to better detect ripe fruit. Others refined their sense of smell. Still others, like certain rodents, learned to cache fruit or seeds for later consumption, inadvertently planting dense pockets of vegetation. Evolution rewarded plants that produced fruit attractive enough to be carried, and rewarded animals that became skilled at finding it. But fruit was more than bribery. It was opportunity. Fruit-bearing plants grew faster, colonized disturbed areas more efficiently, and formed dense canopies that changed the temperature and humidity of ecosystems. Forest edges, once sparse, thickened with shrubs and saplings deposited by birds. Riverbanks flourished where seeds arrived in the droppings of thirsty animals. Even grasslands were shaped by fruit-bearing shrubs claiming patches of soil disturbed by grazers. Some fruits grew enormous, the botanical equivalent of billboards. Think of ancient plants producing giant, fragrant pods or brightly colored drupes designed to attract the largest herbivores of their time. Others shrank into tiny bead-like structures perfect for the nibbling habits of insects or tiny birds. Size did not matter. What mattered was persuasion. What made fruits truly remarkable was their dual nature. They were both gift and deception, generosity wrapped around a subtle request. Carry me, move me. Let my lineage reach places I cannot go myself. Animals accepted the trade willingly. By the time they realized the deal, they were miles away and leaving the next generation of plants in their wake. Fruit did not simply appear as a bonus on the evolutionary stage. It redefined the stage entirely. It connected mobility to reproduction, taste to survival, color to opportunity. It scattered plant lineages across continents, and created new webs of dependency and abundance. Plants had mastered the art of bribery with astonishing finesse. As flowering plants diversified and reshaped ecosystems with vibrant colors and tempting fruits, a quieter revolution began at ground level. One that did not rely on height, beauty, or elaborate partnerships. Instead, it relied on something far more understated: adaptability through humility. Grasses, with their slender leaves and unassuming structure, stepped into a world of shifting climates and restless herbivores and rewrote the rules of life on land. Where forests faltered, grasses found opportunity. Where disturbances toppled others, they rose again with astonishing speed. Grasslands began forming when parts of Earth grew drier and more seasonal, especially across the late Cretaceous and into the Cenozoic. Forests, once vast and continuous, broke apart in regions where rainfall became unpredictable. Lightning storms sparked fires that swept across dry vegetation. Large herbivores roamed in growing numbers, stripping available foliage and trampling soil. These were environments where plants faced constant disturbance, places where any species relying on stability would struggle. But grasses did not simply tolerate disturbance. They embraced it, weaving it into their strategy for survival. The first key to their success lay hidden underground. While many plants invested energy in building tall structures or broad canopies, grasses developed dense, fibrous root systems that formed intertwined mats just below the surface. These roots held the soil tightly, even when fire or grazing removed everything above ground. They served as nutrient reservoirs, water collectors, and anchors. When rains returned or grazing herds moved on, grasses regrew with startling efficiency, producing fresh shoots that seemed to rise almost overnight. In a world where unpredictability reigned, grasses mastered the art of being perpetually prepared. Above ground, they adopted a growth pattern unlike any seen before. Most plants grow from the tips of their stems, a vulnerable position when something hungry comes along. Grasses, however, shifted their growth zones downward, hiding them at the base of the plant, safely beneath a protective sheath of leaves. This adaptation meant that herbivores could nibble, chew, or graze the visible parts without harming the plant's ability to recover. Even fires that scorched entire landscapes rarely reached the growth points nestled at ground level. Grasses essentially redesigned themselves so that losing their tops was an inconvenience, not a catastrophe. Fire, far from being a threat, became one of their closest ecological allies. When flames swept across the land, they consumed dry stems and leaves, returned nutrients to the soil as ash, and cleared away taller competitors that could overshadow grasses. Once the smoke dissipated, the plains transformed into vast, open canvases ready for regrowth, and grasses, already poised at their growth bases like runners waiting for a signal, wasted no time in re-establishing their dominance. These recurring fires ensured that the landscapes remained open, sunlit, and ideally suited for grass proliferation. Their reproductive strategies matched their resilience. Many grasses relied on wind pollination, a method that required neither color nor fragrance, allowing them to flourish in open environments where breezes carried pollen across impressive distances. They produced seeds in abundance, each one small, light, and capable of being transported by gusts or picked up inadvertently by passing animals. Some species developed awns, tiny twisted structures that helped seeds burrow into the soil using only the humidity of the air and the shifting of the breeze. Others coated their seeds in nutrients appealing to foragers, turning animals into accidental seed planters as the remains were dropped across the landscape. As always with plants, persuasion came in many forms. Herbivores, which had once posed dangers to other vegetation, became integral partners for grasslands. As grazing mammals increased in number and diversity, eventually including great herds of ancient horses, antelope-like species, and roaming megafauna, their feeding patterns shaped the plains. They clipped grasses short, but rarely destroyed them. And their constant movement prevented forests from reclaiming open territories. Their hooves pressed seeds into the soil, aerated the ground, and created the very disturbances grasses needed to thrive. By evolving alongside grazing animals, grasses turned consumption into collaboration. Even their leaves told a story of adaptation. Grasses developed silica-rich tissues that made them tough and abrasive, an evolutionary deterrent that wore down the teeth of herbivores. Yet this too reshaped the world. Grazers with teeth better suited to grinding evolved in response, and their success further expanded grasslands. In essence, grasses sculpted the animals that fed on them, teaching entire lineages how to adapt to life in open, windy plains. Each bite shaped both herbivore and plant, a quiet tug-of-war that forged new ecological pathways. As grasslands expanded, they created ecosystems defined not by towering giants or dense shade, but by openness. Here the horizon stretched unbroken, and the sky felt impossibly vast. Winds swept across waves of green and gold that shimmered like water. Rainstorms arrived dramatically, feeding soils that burst into new growth almost immediately. Dry seasons returned the plains to muted browns, only for life to surge back with renewed vigor once moisture arrived again. This rhythmic, pulsing cycle became the heartbeat of grassland ecosystems. The presence of grasses also transformed Earth's climate. Their dense root networks sequestered carbon in soils, cooling the planet over long timescales. Their regulation of water flow shaped river systems, reducing erosion and helping stabilize floodplains. Where once forests dominated, now grasses established continents, spanning biomes that influenced weather patterns, migration routes, and the evolution of countless species. Yet perhaps the most remarkable aspect of grasses was their simplicity. They did not rely on towering height or elaborate structures. They did not bribe animals with fruit or sculpt the air with fragrance. They thrived by being tough, flexible, and ready for loss. They turned disturbance, fire, drought, grazing, into opportunity, and in doing so, demonstrated that resilience can be as transformative as ambition. By the time grasslands reached their fullest extent, they had become one of the most influential ecosystems on Earth, vast, dynamic worlds built on endurance and renewal. By the time modern forests took shape, Earth had already weathered countless eras, oceans rising and falling, continents wandering into new arrangements, climates shifting with glacial patience. Through all these transformations, plants had accumulated a library of evolutionary strategies, the tenacity of mosses, the subterranean craftsmanship of roots, the vertical ambition of early vascular giants, the endurance of conifers, the charisma of flowers, the cunning of fruits, and the resilience of grasses. Modern forests became the quiet synthesis of these long, intertwined histories. They were ecosystems where each tree, shrub, and fern carried ancestral memories in its tissues, forming landscapes that felt less like collections of organisms and more like slow-moving, living archives. In these forests, structure became art. Vegetation organized itself into layers, each one tuned to different light, moisture, and nutrient rhythms. The emergent canopy reached skyward with vast, sun-catching crowns, broad leaves unfurling in geometric mosaics, needles stretching toward high-altitude winds, and branches interlacing like the vaulted ceilings of natural cathedrals. These giants negotiated with sunlight directly, absorbing energy that powered not only themselves but entire ecosystems below. They moderated temperatures, softened winds, and transformed harsh midday light into gentle, dappled patterns that shifted like living constellations on the forest floor. Beneath them, the understory unfurled in partial shade, a world quieter, cooler, and far more intimate. Here grew shrubs, saplings, and shade-tolerant herbs that had perfected the art of living in borrowed light. Their leaves were broader, thinner, and arranged with meticulous efficiency to capture even the faintest beams sneaking through the canopy above. Some plants waited patiently for decades in this tier, gathering just enough energy to persist until the rare moment when a fallen tree opened a window of sunlight. For them, patience was a competitive strategy, and time, long, deep time, was almost a companion. The forest floor, though dim, was anything but static. It formed a realm of decomposers, detritivores, and life crafted from remnants. Litterfall, leaves, bark, twigs, fruit husks, settled in soft layers that cushioned footsteps and muted sound. Fungi spread through this organic tapestry with filamentous threads, weaving hidden networks that connected everything from towering trees to the smallest seedlings. Through these networks flowed nutrients, warnings, and chemical conversations so intricate they resembled the whisperings of an ancient underground parliament. While not conscious in any traditional sense, forests demonstrated a form of distributed awareness, a responsiveness to stress, abundance, and change that emerged from countless subtle interactions rather than any single intelligence. Roots, long-practiced artisans of the soil, added their own complexity. They spread outward and downward, forming vast webs that intertwined across families and species. In some forests, the roots of neighboring trees fused or cooperated, sharing water during droughts, or passing nutrients to shaded companions unable to photosynthesize enough for themselves. Such generosity might seem improbable in a competitive world, but forests evolved not only through rivalry, but through quiet collaboration. Species that could coexist, balancing growth rates, resource use, and seasonal rhythms, formed more stable ecosystems than those ruled by singular dominance. Diversity became a stabilizing force, a biological negotiation where each plant found its niche. Moisture cycled through these ecosystems with elegant precision. Trees inhaled water through their roots and exhaled it through leaves, sending plumes of vapor into the atmosphere that influenced clouds, rainfall, and regional climates. Forests effectively became rainmakers, generating their own weather patterns. They captured fog on leaf surfaces, guided runoff into streams, and held water in spongy soils. This hydraulic choreography shaped landscapes far beyond the forest boundaries, feeding rivers, sustaining wetlands, and regulating temperatures across entire continents. Animals, drawn into these layered worlds, formed partnerships and tensions that enriched the forest tapestry. Pollinators navigated three-dimensional labyrinths in search of blooms. Birds perched high in the canopy scattered seeds through shifting air currents. Grazers browsed on tender shoots, guiding the regeneration cycles of plants. Predators hunted through shadows, shaping animal populations that, in turn, shaped vegetation patterns. Every movement, every interaction contributed to the forest's ongoing refinement. Even disturbances, storms, fires, landslides, insect outbreaks, played essential roles. They opened gaps that rejuvenated growth, redistributed nutrients, and encouraged species that relied on periodic disruption to complete their life cycles. Modern forests, though ancient in lineage, thrived not by avoiding disturbance, but by weaving it into their long-term rhythm. Where a fallen tree created decay, it also created opportunity. Where lightning ignited a patch of woodland, certain seeds awakened. Death and renewal became two sides of the same endless mosaic. What made modern forests true timekeepers, however, was their scale and longevity. Some trees lived for centuries, stacking year upon year of memory in their rings. Whole groves persisted for millennia, migrating slowly upslope or downslope with changing climates. Species turnover unfolded over spans of time so vast that an individual human lifetime felt like a fleeting breath against them. Forests recorded droughts, floods, volcanic eruptions, and even the migration patterns of early mammals. Their wood bore histories written not in ink, but in density and hue. Standing in such a forest today, whether among the towering hardwoods of temperate regions, the mist-laden trees of cloud forests, or the tangled giants of tropical rainforests, one feels the depth of this inheritance. Every rustle, every shift of light, every earthy scent rising from the soil is the outcome of hundreds of millions of years of quiet refinement. Plants have stretched, shrunk, diversified, and persisted through unthinkable time to build these layered worlds. Forests embody patience. They expand and retract with climate, adapt to new companions, recover from wounds, and continue their slow conversation with the planet. They are living timekeepers, not because they measure time, but because they become it, accumulating ages within their trunks, roots, and soils, turning evolution into something visible, tangible, and deeply grounding. Here, in their cool shade and filtered light, the journey of plant evolution reaches a kind of peaceful culmination. A world shaped by quiet resilience, subtle cooperation, and the steady, almost meditative persistence of green life.